Okay, good. So we were here. We were speaking about vectors. So now we will continue with this topic. Okay. So we gave an example in two dimensions for summating vectors. Again, and another example in two dimensions for computing the inner product. And then we have to say that we can demonstrate that this inner product is a number which corresponds to the magnitude, so the length of the arrow, let's say, of the vector A, multiply the length of the vector B, multiply the cosine of the angle between the vector A and B. So this thing for us is important because at a certain point we will speak about so-called orthogonal vectors. So vectors that are orthogonal each other have an angle measured in radians of half pi, so 90 degrees, let's say. So in one circle there are 2 pi radians, so pi half corresponds to 90 degrees. So those vectors having this angle between them, let's say themselves, they have a so-called inner product, also called scalar product, equals to 0. So when you meet two vectors having inner product 0, it means that they are orthogonal each other. So another important thing is to consider the so-called projections. So we already informally introduced the notion of projection. So you see here a vector A, and then I draw these little dots here and meeting this other axis, and then I consider this little piece of axis to be what I call the projection of the vector. So of course projection is something that comes from geometry. So let's say here you have the sun, which is let's say illuminating this tower here. This is the Leaning Tower of Pisa. So let's say it's a vector like this. Now it's not leaning enough, so I can probably magnify it like this. So if the sun here is illuminating this downwards, then there will be a shadow here, which is the geometrical projection. So it tells us how much in that direction the tower is leaning. So when we speak about projections, for instance here, let's identify this direction with the direction x and this direction with the direction y, again in two dimensions. So projections are important because they tell us that this vector A can be composed, or if you prefer decomposed, by the summation of two other vectors, one in the direction x, the other one in the direction y. In other words, A is made a little bit of x plus a little bit of y. To be more precise, we have to say that this x and y would be unitary vectors, so vectors pointing the direction of the axis but having unitary length. So the length of those vectors that are defining the direction are 1. And if we want to calculate the length of those things here, like this projection, we can do this by calculating this thing, which is an inner product, so something we have seen so far. So to summarize the concept, by taking the inner product between a vector and another vector having unitary length and pointing towards an axis, for instance this axis, we get what is called the projection of the vector A on the axis, which is pointed by the vector u. So this is the mathematical operation to compute this. Another important things to keep in mind is the concept of a normalization. So what does this mean? It means that sometimes we want to have a vector. Again, let's take advantage of this drawing. So the vector A, this one, and sometimes what we want to have is a vector having the same direction of this one. So now I draw the direction as a straight line. I hope you can see. Maybe it's too faint. Let's change color. Let's do it in black. So sometimes we have a vector and we want to transform it into another one having the same direction but unitary length. So let's say maybe something like this. It can be also bigger, depends the size of the unit we choose. So this process is called normalization. So how can we do this? It's simple. We can demonstrate that if we take a vector and we divide each of its components by its magnitude, then we get a vector having the same direction but magnitude 1, which is what is written here in this formula. So if I go back one slide, then we see also something, maybe I missed to say this, that this operation of computing the inner product, so these long summations if we have many dimensions, also corresponds to have also corresponds to the magnitude of the vector raised to the power of 2. So which means that if we want to compute the magnitude, the length of a vector, you have to take the square root of the inner product of the vector with itself. So if we do this and we want to compute the magnitude of a vector, we obtain it by taking its components and individually dividing them by its length. So we apply the definition of inner product. We can carry this 1 over a as a common factor out of the vector, from the left vector, which is the row vector, and from the right vector, which is the column vector. Here we have these two factors. Then what remains is the inner product, which is between those and those other numbers here, which is written here. So, but this by definition is exactly a square, and we have I write here the square root of 1 over magnitude of a multiplied magnitude of a, so a square multiplied this thing, which by definition is a square, and this thing is the square root of 1, because this thing simplifies, and this thing is 1, which is this. So we have seen addition between two vectors, inner product, projections, and also a process which is called normalization. So the transformation between a vector to a vector having same dimension but length equal to 1. Okay, let's go on. So with those elements in mind, we try to reword the things in a more precise way. So we said that a vector can be written or drawn, let's say, within a reference frame. So this leads us to the concept of geometry, which is called vector space. So vectors are things that stays in a place, which is called a vector space. So we need to define the axis, and once we define the axis, we can plot a vector on that reference frame. So here we introduce another symbol, which is this thing, delta. It's called Kronecker delta. It's just a symbol. So it's a symbol having this meaning. So let's zoom it a little bit. Delta ej. So this thing is 1 if the index I equals the index j, and 0 if the index I is different from the index j. So it's a number having two possible values depending on the values of those two indices. So again, it's just a symbol to write long things in a short way. And for instance here, what does it mean? It means that if we consider a collection of vectors u1, u2, u3, and vectors un, those vectors are unitary vectors, so we chose vectors having length 1 each of them, but they are in different directions. So we can consider vectors, specific vectors, having these properties, that the inner product between a certain vector ui can be u1, u3, u11, I don't know, something. I is just an index spanning from 1 to n, as well as j. So this thing, writing this, means that we are choosing vectors which are orthogonal each other. Why? Let's see how this symbol works. If I take ui and then I take uj with j equals I, so let's say ui multiplied ui, this thing says that this inner product is 1. That would be the length of ui, the first vector here, which is 1, because we said we want unitary vectors, ui, multiplied the vector of uj, and we said that we are analyzing the case I equal to j, so uj is ui, 1 by 1 multiplied the cosine between the two vectors, but these two vectors are the same because we said that I is equal to j. So the angle of a vector with itself is 0, and therefore the cosine of 0 is 1. So this inner product here in this case is 1 by 1 by 1 and makes 1. If we choose a vector which is orthogonal to ui, so a different j, then if they are orthogonal, this inner product is 0, and this symbol works like this: delta of ij, if I is different from j, is 0. So complicated things to say this thing, for instance. So we go to our blackboard here, scratch notes, so let's take two-dimensional simple case. Let's define a vector u1 and the vector u2. The vector u1 as the vector having 1 as x component and 0 as y component, because it's completely parallel to the x-axis. The vector u2 is the vice versa, is vertical, so it doesn't have an x component, so its x component is 0 and its y component is something different than 0, and we make it equal to 1 in order to have the length of it equal to 1. So first of all, let's verify this just as an exercise. Let's calculate u1. So we say we take the row version of the vector u1 and we multiply by the column version of it. So this by this, 1 by 1, plus this by this, 0 by 0, makes 1. And then if we take square root of 1, this is 1. So the length of u1 is 1. Length of u1 is 1. And similarly for u2. I don't repeat this, it's exactly the same thing. So these are two unitary vectors. Let's verify they are orthogonal each other. So let's calculate the inner product between u1 and u2. So this time is the row version of u1, so 1 0 multiplied the column version of u2. So we have to be careful because u2 is 0, 1, so it's 0, 1. Notice the difference here, it was 1, 0, because that one was the vertical version of u1. So if we do this, then we have 1 multiplied 0 plus 0 multiplied 1, and this is simply 0 plus 0, which makes 0. And just to be clever, we compute the magnitude of this thing, which is the square root of 0, which is 0, of course. So those two vectors are orthogonal each other. So I go back. Back to the slides. So this is what we are doing here, but not just with two vectors, u1 and u2, not with 3 like in 3 dimensions, but with n in n dimensions. We're supposed to have a sort of strange multi-dimensional space where we have n vectors, each of them with unit length, each of them orthogonal to each other. This is what we are writing in a single thing when we say this. Similarly, we can say that a vector living in so-called n-dimensional space is again composed about the summation of its projections, which are those things here. This is what is written here. A1 is the projection. And so we arrive to a concept that a vector, any vector in its dimensional space, can be composed by the summation of its projections on the axis defined by the reference frame. So this thing, believe it or not, is the fundamental thing in order to describe signals. We will see how.
Excuse me, can
Yes.
you hear me?
Yes, yes, please.
Can you just repeat the last sentence about the last equation?
Okay, let's go back. So, I'm sorry, but I don't remember which was the last sentence of mine.
The one with the purple color. Yeah.
This one here.
The number 1.5.3.
Ah, okay, sorry, this one. Okay, so what I was saying here is just what we have seen in 2 dimensions, and it still holds in n dimensions, even with n to be infinitive. So what's written here is that these numbers a1 or a2 or a3 or an are the projections of the vector a onto an axis which is labeled by n and indicated by a unitary vector un or u3. So, and by summating vectors which are directed with the elementary directions u1, u2, u3, un, multiplied by a coefficient which makes these vectors becoming longer or shorter in that direction, by summating those vectors together, we can recompose the original vector. So now I do a drawing, so maybe it will be more clear. So it's a sort of tautology what I'm saying. So I'm saying the same thing in different ways. So in 2 dimensions it's like this. I consider 2 unitary vectors u1, u2. Then I consider any vector, for instance, let's say this one. I call this vector A. Then I want to give a different expression for A, so I consider the projection of A on the y-axis and the projection of A on the x-axis, and this is the projection. I call it AX, and this is, sorry, AY, and this is AX. So AX is a number, but it can also be this specific vector here. If we consider, let's say AX, let's put it with this symbol as a vector. So this thing is a length AX multiplied a unitary vector, sorry, let's write it like this, u1, which we write like this. Okay. And what we are saying here is that we can make this vector to be like this, AX u1 plus a similar vector which is AY u2, where AX is, the projection of the vector A on the axis u1, and AY is the projection of the vector A on the axis u2. And therefore this thing is something like this. It's a number which is A1 U1, let's say, multiplied by a direction U1. Oops, now I don't have space. So I continue here, plus A1 U2 multiplied a direction U2. Now I didn't write very carefully, but if we go back to the slide, this is what is written here. So A1 is this thing, A2 is this other thing, and so on. So it's the rule of the parallelogram in n dimensions. So this vector here is this vector, the projection, plus this vector. This plus this makes this. If you do this graphical thing that we have done here, let me go back, where was it? Here. Okay, it's the same thing, but now we have specific vectors which are not any vectors, but vectors aligned along the axis, which are also called the versors, the ones that gives the direction of the axis. Okay,